because now we are going to demonstrate the very popular examples using RS5, that is a filter examples, filters design. Okay, so here is the aim is the design and simulation of IF band pass filter, which is running on the 70.7 megahertz band. There are three popular IF: 70.7, 455 kilohertz, and 10.7. So three popular IFs are there. Generally, if you see this application client of Tata Sky, which working on 14 gigahertz. Here is the horn antenna is there, corrugated horn antenna. So whatever signal coming on from the 14 gigahertz take catch by antenna. And here is in the black box there is a circuitry called as a low noise block converter, LNBC. This LNBC is having amplifier plus mixer, but after mixer there is an all image frequency is generated, and this image frequency is have to be filtered out by kind of filter, and that's why the IF band pass filter, a small RLC filter they are putting to extract only the 70.7. So in this black cable, coaxial cable, the 70.7 megahertz is going to your Tata Sky DTH box. So that box is only entertaining 70.7 megahertz. To do this, we require a band pass filter. In the band pass filter, we are more conscious about this roll off side. In the start side or in the end side, we have to make sharp, very sharp, so that only our band could be entertained, rest of the frequency is not going to be entertained. Here you can see this, to do this roll off very high or very sharp, we required LC like these kind of combination. Instead of giving a single combination, we are giving two of the pairs combinations are there. And here you can see this is a 1 2 3 4 and 5. So this is a 5 order filters is going to be designed to make this roll off very sharp, so we are getting only the 70.7 or 70 megahertz, and rest of the frequency are get attenuated lower side and upper side. Here the specifications are: center frequency 70.7, type bandwidth Butterworth filter, order of filter is 5, impedance is 50 ohm, and this is the table coming from the POSAR for the GK and LK coefficient, that is order is 5. That's why we have to take this for first element 0.618, second element 1.68, third 2.0, fourth again repeat 1.68, fifth again repeat 0.68. Means even 1 2 and 3 calculations you done, rest of the calculation is copy and paste. So this is the very good structures of the periodicity. So that is in repetitions of these two elements, same like first and second and fourth and fifth. So we now design this filters. In the design step, the first conscious point is a fractional bandwidth, that is the delta. Means higher frequency minus lower frequency upon the center frequency is your delta, and that is a fractional bandwidth. And by using a fractional bandwidth, you have to calculate the inductance value, capacitance value. These are the formulas which are given to calculate the series inductance, series capacitance, parallel inductance, parallel capacitance. And in these all formulas, only the components called as GK, which is coming from the table, R is 50 ohm, delta is the fractional bandwidth, omega is the 2 pi f. So here also fractional bandwidth 2 pi f, GK means the coefficient coming from the table, and R is a 50 ohm. So this all formulas are considering only these factors. And now in our diagram also you can see L1, C1, L2, C2. L1 means LK1. So K factor is replaced by 1. Then C1 is replaced by 1. If it is parallel, then again L2, C2 factor you have to take 1. First we have to calculate the fractional bandwidth, that is F2 minus F1 upon F1 plus F2, and that is 0.1432. Here we are considering for 72 megahertz, we are considering almost 3 megahertz upper side and 3 megahertz lower side, and that bandwidth constant we are coming. This is second factor is omega, that is 2 pi f. This is the total coming. Low pass prototype values are 0.618, 1.62, again 1.68, 0.68. So L1 formula is basically the GK. Same GK we have to copy, paste. Then R is the 50 ohm, that 50 ohm is there. Then again 0.143, that is a fractional bandwidth, and your omega 0. So you will get 492 nanohenry. C1 formula is fractional bandwidth upon omega 0 GK into R. So that is your GK is this 0.618, R is 50 ohms, so omega 0, and this is your fractional bandwidth, so you are getting in a such a way that you have to calculate L2, C2, L3, C3. After that, I already told that they are repeated. C5 is equal to C1, L5 is equal to L1, C4 is equal to C2, and L4 is equal to. Now same things we done in our RF Spice software. Okay, so this is the software I am opening. First we are going to attend the basically network analysis. In the network analysis we have to keep the on the both port we have to keep the network. So press Alt N. So this is the P1 port, and second is Alt N, second port P2. So this P1 is there and P2 is there. In between your capacitors, everything circuit is there. In fact, even if you not put a 50 ohm, these loads are actually made for the 50 ohms. Even if you don't require, you can delete also these lines and you can directly connect. And here also you can delete these lines and directly connect basically this port to direct on the lines, because these lines are matched for the 50 ohm. So go to network analysis, go to setup. Okay, now this node is P1 and P2 we are selected. This P1 selected and P2 is selected. So after that sweep is from 30 megahertz to 100 megahertz. This is 100 kilohertz output. Cartesian S parameter and decibels, and say run. Okay, in the single side we can on, and we can see this graph is there. Okay, okay, here is we are getting this value basically. uh, Now you can see this is the flat band we are achieving basically at 70 megahertz. This is our center frequency 70 megahertz, and this flat band you can easily achieve over here this filter. So now we just zoom this filter to calculate the 3 dB bandwidth. Okay, and now we will check the center frequency. The center frequency is basically 69.71, but we design at 70.7, but theoretically and practically there is somewhat differences there. So it is come to say almost come to 70 megahertz, and the insertion loss is minus 16.9, that is the 17 dB insertion loss is there. If you add 3 dB, means to calculate the 3 dB point we have to go for the like 17 plus 3, that is a 20 dB, and 20 dB. So we if we add this at a 20 dB, we go at higher side. Okay, 20 dB, and this is your start frequency. 66 megahertz is your start frequency, and at the same time if you go here almost 72 megahertz. Okay, 72 megahertz your stop frequency. So that is a 6 megahertz bandwidth you are achieving from this to this, and the center is 70 megahertz. Even if you want to calculate a 20 dB cutoff point, that is 20 dB cutoff point means 16 and 20, that is 46, that is 36, no? 36. So that is a 36, so that is a 20 dB down point if you calculate, and that frequency is a 62.23, means within a 8 to 10 megahertz from the center to 62, that 8 megahertz, within 8 megahertz your 20 dB is going to be decayed. So this is very sharp roll off we are achieving. Within a 8 megahertz your 20 dB is decreasing. Even if you zoom backside, so you are getting here the sharp cutting is there. here is somewhat slow at the lower side, but higher side it is very sharp. So in the S21 we calculate the center frequency as well as the cutoff points are there. Now we proceed to this other parameter. You can also check the Z parameter of the same filter. Even in terms of amplitude you can check, or you can check in the real terminology. Okay, so here is your Z parameters. We can go in the trackers, that Z11 we are going to be off because only we are interested in a insertion parameters. That insertion parameters you can look here, the Butterworth somewhat positions are there. Okay, okay, so here is one deep is coming, and this is actually the Z parameter variation handled by your filter. So this is the natural graph of the impedance trends, which is just shown by this plot. Even if you go in the next plot, that output side for the real imaginary, you can see also the Cartesian y parameter, y parameter, s and z parameter you can observe. We can go for the next testing, that is called as an AC sweep test. AC sweep test, we can also open the one more our RS spice, where we make the same circuitry, only the 50 ohms loads we are going to be adjusted over the both side. Here I am putting a sine wave source. If you double click this source, you can see this 1 megahertz frequency is there. Nothing is do, just click on OK signal. Rest of the circuit is fine, and go to test, click on AC, click on setup, 10 megahertz to 100 megahertz, step is 100k. So go to graph, and the graph you can select, this is the graph. P2 you have to select to check the output. Even P1 is not necessary, you can remove, only you put dbp2. Okay, and if you go and say run the graph, okay, here you can see find on 70 megahertz, this is 100 megahertz, this 0 megahertz. Even you can go in the edit axis, go to the bottom side and click on the logarithmic, so you can find these all frequencies: 60, 70, 80, 90, 100, and here is your frequency. But the best of the thing is about the your AC sweep parameter is not only that, but you have to click on the sweep setup. So if you click on the sweep, it will ask about the sweep setup. Sweep setup means you can find out, or you can study the your all components. Suppose these are the component. If it is varied, then how it is going to be affected. First I will show the effect on the R1 and R2, that resistance, R1 and R2 resistance, or inductance also we can take care. So this is my R1 resistance. I can take select R1 resistance, say sweep parameter, say 20 to 10 to 70. These parameters are there. Though so say only accept change, so the accept change, only the 6 readings are there, and click on OK. So I am giving you the effects. If this source resistance vary, how your pattern is get vary. So go to preset graph, select only, okay, only VBDW select, remove, or you can go for the new plots directly. P2 you have to select, add it and say OK, and go to run button. So if you see, this is the variation happen due to your load resistance. If the load resistance it get varies from 10 ohm to 100 ohms, in the slower part, that you can see the insertion loss get increased, at the same time your bandwidth is get affected. So this is the happening. Even you go in the bottom axis, say bottom axis, and click on the log, you can see the better. So here is the insertion loss is decreases, but at the same time the bandwidth of the your filter increases. If you vary the source resistance, this is the impact. If you vary the like go to sweep parameter and select some another sweep parameter, like let's say capacitor C1. If I select a C1 capacitor and go to select a C1 capacitor, and select this range is 10.6, so we put 1 picofarad to 100 picofarad, and here is the 10 picofarad. 10 picofarads are there, so accept change. So there is change. This resistance I deleted earlier, only the capacitance are there. Click on OK and say run. So if you vary the capacitance, then your center frequency is going to be shifted. You can observe this is in this plot. So this is the frequency, this center frequency shifted, your graph flatness is over, your Q factor is going to be vary. Everything is happen if you vary the capacitance effect. In fact, you can vary multiple, means more than 2 setup also you can vary, like one C1 capacitor plus some inductors if you want to vary, like 492. Say sweep parameter like from 400 to 500, that is your nano. Nano here is also I have to keep it a nano, and the step is 25 nano. Okay, accept change. So if I click OK, so at a time I vary the two parameters. One is about our capacitor and second the inductor. Now you can see this is the capacitor already we vary, and this is the effect coming due to the your inductors. So two or more parameter you can vary and see the effect of the filters characterization by using AC sweep analysis. That's why in our software we are not only providing a single analysis, but we are providing a bunch of analysis to get the awareness about the circuit from various dimensions in the RSPICE. Here you can see this various effects happens over your practically. Even you can stop this if you don't want to run this experiment. So this is the stop button is there. Now okay, it's still running, so you can stop it here also. So in this way we found that by using AC sweep analysis or just basic sweep we can found a pattern, but by using a sweep parameter we can vary the things and we can see the thing. And the last which is important, called as a Monte Carlo analysis, which is for particular aim, where we have to define our model parameter, user defined parameter, and we have to set the tolerances, and we can achieve the particular roll off or particular gain from this pattern. This is for the optimization purpose, this is for the parametric purpose, and this is for the testing purpose. So these three setups are we are providing. Not only that, but also we found that in our early stage that network analysis is there, Z analysis and S parameter analysis we done of that filter. So AC sweep and network analysis, by using this you can find out the performance of your band pass filter. Thank you.